This is the one I've been waiting for. In this diagram, at least initially, I've got my ground, I have my ramp, and this is angle A, this is my 20 degrees. Side A is 30, side B is 40. 40 is going to be the length of my ramp. And side A measures 30. Now here's what we haven't worked a triangle like this yet. We haven't worked a triangle yet where the angle measure that was given to us was less than 90. The previous problems were both these kind of gigantic angles, obtuse triangles we ended up with. In this one, I don't know if I should, do I draw my 30 for my side A, do I draw it into here? Will the side length of 30 actually even reach the ground, as I like to call it? Maybe the 30 is going to reach the ground, but it's going to have a bunch of extra, in which case, well, let's not use that. Maybe the 30 should be drawn in here. I think it's going to be one of these scenarios, or I suppose the 30 could conceivably actually just come down here and it could fit perfectly between the end of my ramp and the ground, just hanging straight down and touch the ground perfectly. How am I supposed to determine that? Well, if you use this analogy of hanging a rope off the end of a ramp, the only way I'm going to know if the rope is even long enough to reach the ground is if I knew the distance from the end of the ramp down to the ground, and we're going to call that h. So the first thing I'd like to do is solve for h. So step number 1, and I think we can put that, let's put it over here. Excuse me. Step number 1, find h. This problem is a little bit lengthy, okay? We might even end up drawing 2 diagrams and having to go through 2 solution processes. So stay organized, keep your pencil sharp, try to use, I'm pretty familiar with this problem. I'm going to find h along the top part of the page, and then if all goes well, I'm going to use the left side of the page for one diagram and the right-hand side of the page for the other diagram, if this problem's going the direction that I think it is. So let's find h. How do I do that? Well, if we assume it's not really an assumption. If we just draw the height into the diagram, where this is still our 20 degrees, and this is a 40, we can just use one of our regular old trig functions in order to solve for h. Look at the 20-degree angle there. The h is opposite that angle measure, and the 40 is the hypotenuse. So that's the sine function. The sine of 20 degrees is equal to opposite, which is h, divided by hypotenuse, which is 40. Multiply both sides by 40. And that's equal to h, which I'll take up here. That's an arrow. It's not an arrow, it's a blob. And then I'm in my calculator. Let's use the scientific calculator this time. Clearing a couple of times. I'm going to make sure that I'm in degree mode. Yep, I see the little DEG there at the top of the screen. And I'll type in 20, and then I'll hit the sine button. That gives me 0.3420, blah, 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 times 40 equals, and I've got 13.68. That's good enough for me. So the height that the ramp is above the ground is 13.68. And the length of my rope, which is my A value, is 30. So do I have enough rope to reach the ground? Definitely. Plenty. More than twice as much rope as I need. Again, the length of the rope is 30, and the height above the ground from the end of the ramp down to the ground is only a distance of 13.68. So So we will be able to draw at least one triangle. Now here's the other question. Can we draw two triangles? Now that I know that the length of my rope is long enough to reach the ground, my next question is, what do I do with it? Do I take these, let's say feet, do I take these 30 feet worth of rope and pull them in here underneath the ramp? Or do I take the 30 feet, don't draw this into this diagram because it's going to look too muddled. Or do I take the 30 feet worth of rope and pull it out away from the ramp? You've got options. You could do either one. So we call this the ambiguous case because we don't really know what to do with the rope. Do we create this triangle where we pull the rope under the ramp or away from the ramp? We're going to diagram both of them. So let me get rid of those two lines that I just drew. And I'm sorry not sorry to tell you all of these things based on this one diagram, but I have to point this out. If the length of the rope, instead of being 30 feet long, what if the rope was 50 feet long? I could definitely, I'm going to make myself some room to draw this. I could take this rope. Now remember, the ramp is only 40 feet long. Look at the diagram. The ramp's only 40 feet long. If I've got a rope that's 50 feet long, I've got to pull that thing way out here in order to close my triangle. There would be the 50. Could I take that 50-foot long rope and pull it under my ramp? Well, the ramp's only 40 feet long. You try to take that 50 feet worth of rope and pull it in here underneath this ramp, and it's going to have a sag to it. You won't be able to pull it so that it's taut, so that the rope is straight. So if the length of, where I'm going with this, in case you were wondering, where I'm going with this is, if the length of your rope is longer than the length of your ramp, you won't be able to pull it under the ramp. Best you could do is pull it away from the ramp and create this really kind of wide triangle by pulling it out here. Okay? That's not the scenario that we're in. The scenario that we're in is this. Let's see. I want to make sure that I write this correctly the first time. The length of our rope, which is A, is longer than H, but is less than the length of our ramp. Okay? This is the height of that the ramp is above the ground. This is the length of the rope, and this is the length of the ramp. So again, if the length of the rope is between the height above the ground and the length of the ramp, then we're working with an ambiguous triangle. We will have two triangles. Is that written somewhere that I could reference it instead of just being part of that kind of crazy description that I just gave you? So A is the length of the rope. You can see it being pulled in two different directions there. B is the length of the ramp. There's your angle measure A. And A is greater than H, and A is less than B. Therefore, two distinct triangles are formed. And you can see the calculation of the H value there. It's equal to B times the sine of A. And you can bet that that's what we just finished doing down here. Two triangles. Let's draw two triangles. Can we zoom out far enough to split the page immediately? Some of it anyway. I was hoping that was going to snap and make a straight line. Let me try it one more time. No. Why would it do that? Didn't work that time either. Okay. Triangle number one, here we go. For the first triangle, I'm going to draw the one where we pull the rope away from the ramp. So I'm going to have my ground is going to be here. A is coming up here. Or sorry, the ramp is going up there. Angle A is over here. Okay, so here's A, which is the 20 degrees still. Let me zoom in on this. And side length A measures 30. Side length B, the length of our ramp, is 40, which means that this is angle B over here, and we can label this as C and C. We have 3 pieces of information, which means we need to find the other 3 pieces of information. We're looking for 2 angle measures and a side length. What are we supposed to find first? Notice, here's the pair. We know A and A. And in order to use the law of sines, we need 3 out of 4 pieces of information. We need a full pair, which we have with our A and A, of 20 degrees and 30 feet. And then we need a half of a pair, which is going to be the B's. We know the side length, we don't know the angle measure. So let's solve for angle measure B. Now, I didn't write down any of that thought process. Excuse me. That might be something that you want to write down. And I'm not going to say it again. You can rewind it and watch it again if you'd like to. All right, in order to find angle measure B, and I would like angle measure B to be in the numerator, so I'm going to write the sine of B over B is equal to the sine of A, since we know what A is, over lowercase a. And I guess I'll just work my way down the left-hand side here. Let's plug in our values. We don't know angle measure B, that's what we're solving for. Side length B is 40, equals the sine of 20 degrees over 30. We're solving for B, so let's multiply both sides by 40. And then we'll need to take the inverse sine of both sides. Now, what's the range of the inverse sine function? We talked about the domain of the inverse sine function. It's from -1 to 1. But what's the range of the inverse sine function? I'm remembering the diagram of the sine function, and we only used a portion of it. I think it was just the middle part that went from -π/2 to π/2, which means that the output values of the inverse sine function are angle measures that are somewhere between -π/2 and π/2. Now, I don't think that angle B is going to be a negative angle measure. So B is probably going to be between 0 and π/2. In degrees, that's between 0 and 90 degrees. And angle measure B up there does look like it is somewhere between 0 and 90 degrees. The other triangle that we're going to draw, I don't know why it is that I feel compelled to do this now. I'm like right in the middle of my work. The other diagram that we're going to draw is this one. It's not even that much. We still have angle A. It still measures 20 degrees. We still have a ramp length of 40. This is still going to be angle C. This is going to be side C, but we're going to pull our rope in and under the ramp here. This is going to be angle B, and this is side A, which was 30. Look at angle measure B over here, not between 0 and 90 degrees. That's why it's beneficial to draw this diagram first, so that when you actually solve for B and you get an angle measure between 0 and 90, it coincides with the diagram that you've drawn and doesn't freak you out. I don't want you to be freaked out. I want you to be prepared. So let's keep going with this work here. That was the 40. We're just sort of filling this in. Sine 20 degrees divided by 30 And then we're going into the calculator in order to finally solve for angle measure B. I'm going to do this one in the scientific calculator. I just like the challenge. All right, so I'm going to type in, it's totally inside out, right? I'm making sure that I'm in degree mode, which I am. I'm going to type in the 20 and then hit the sign button. I've got 0.342, blah, 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 times 40 equals, I've got 13.6808 divided by 30 equals 0.456. That is a number that is between -1 and +1. It's in the domain of the inverse sine function. So let's take the inverse sine. I'm going to hit the second button and then the sine button. So I hit second, sine, and I got 27.131. And I am very happy to have finally found that angle measure. I'm putting a box around it so it doesn't wander off. I'm glancing up at my diagram to see that, yeah, I can imagine angle B being 27 degrees. That looks pretty good. Nice. As long as I've got this number in my calculator, let's see, is there an easy way to do that? We might as well find angle measure C while we're at it. I think that we can, I think I'm just going to clear my screen and I'm going to go for angle measure C. Angle C, and you could put the angle marker in front of that B if you want to also. I'm really putting it in front of the C because the capital C and the lowercase c look so similar. So angle C is equal to 180 minus B minus A, which is 180 minus angle measure B we now know is 27.131, minus angle measure A, which was given to us as 20 degrees. So angle measure C is equal to 180 minus 27.131 minus 20. I must have hit a wrong button. 180 minus 27.131 minus, I got negative 54 already. My fingers are not working apparently. 180 minus 27.131 equals 152.869 minus 20 equals 132.869. That I believe. That happens. I had to type it in 3 times just to get the correct value there. Sometimes the fingers don't do what the mind tells it to do. Okay, so we've got angle measure C. What are we missing? We've got A, B, and C for angle measures. We know sides A and B. Those were given to us. We need side C. So it's a good thing we've got angle measure C. We're going to need that as a half pair. I'm going to continue to use A and A as my full pair. And now that I've got angle measure C, we'll use that as our half pair to find side C. Do I have enough room at the bottom of the page to do that? I sure do. I think I will switch colors. And let's just check one more time. All right, so I need lowercase c to be in the numerator because that's what I'm solving for. C over sine C is equal to, and then I'm going to use my A values again over sine A. Cia, there we go, sine A. And side C is unknown, so we'll leave that as a C. In the denominator, we're taking the sine of 27.131 equals side length A was our rope length, which was 30. I believe it was 30. It's been so long. Yep, there it is. Over the sine of 20 degrees. I don't know why that's separated. There we go. Multiply both sides by the sine of 27.131. And then we're going into the calculator again. I'm going to keep going back and forth. I'm going into the grapher this time. And I've got 30 times the sine of 27.131, closing my parentheses, divided by the sine of 20, close, enter, and I got, wow, I got 39.99996. I'm calling it 40. I'm doing it. That's amazing. Side length C is 40? That triangle is not drawn to scale at all then, is it? It's like an isosceles triangle. Side length, if side length C is 40, this should be drawn like maybe here, so that this is 40, and this is already 40, and we got an isosceles triangle. So shouldn't that mean that angles C and B should be very similar to each other? Well, angle C is really big, that's true. So I feel like side C should be considerably larger than 40. I'm not liking this. See how what I'm looking at in the diagram doesn't match up with the numbers that we actually have? This is big 132 degree angle up here, which takes side A and side B, or sorry, that was side B, this is side A, and it sort of splays them apart like this, right? It opens them up really wide. Whoa, there we are. So the distance between my fingertips should be much larger than the 30 or the 40. So we've got to figure out what happened. Is it possible that we just typed it into the calculator wrong? That's possible. That's possible. Oh, I see it. Do you see it? It's an easy fix. On paper and pencil, I would be using my left index finger to point at the value, the number that I'm actually supposed to be using and transcribing down the page. But with this, writing on the iPad, I don't do that, or it'll make the whole thing go bananas. The mistake that I made is this number right here is supposed to be the sine of my C value. However, 27.131 is angle measure B. I grabbed the wrong angle measure. That happens. The good news is that I recognized that side C was so similar to side B that didn't jive with my relatively accurate diagram, and that compelled me to go back and check my work. So that is a good lesson for you to see. So I think I can actually erase some of this stuff. I'm definitely going to erase this angle measure that's in here. We need to make that correct. And that means that this angle measure here needs to go. Everything else I think was actually okay. And then certainly the actual value of that was wrong. So let's write in some correct values here. It's C over the sine of 132.869. Everything else in this equation was correct. The other thing we need to correct was that this needed to be the 132.869. Everything else in that equation was correct. And so now we can go into the calculator again. Let's try this again and see if we get a more reasonable C value. That was a 132.86. Here's insert 9. Enter. I got 64.29 rounded. 64.29. That seems considerably more appropriate. You know, if you took those side lengths that measure 30 and 40 and you opened them all the way up so that it created this 180 degree angle, I can't even bend my wrists that far, right? I could draw it though. So that this was 30 and this was 40. This total distance is 70. So you'd have to take those side lengths and close them down just a little bit so that maybe the 40 was here and the 30 was here. which would take the 70 measure that we had here and make it a little bit smaller. How about something like 64.29? So just double checking again to make sure that my answer of my C value of 64.29 is reasonable. I think it is, so I'm putting a box around it. And we have solved our first triangle of the ambiguous case. Thankfully, and you might be already dreading the fact that we have to go through this process again, but the good news is that we're going to be able to use some of the information from the first of the triangles in this second diagram. So this process is going to be a bit shorter. And the first piece of information that I want to show you is this. Now this is tough to take notes on. I don't want you to think that I don't know that. All the arithmetic that we just did, that's pretty straightforward. But the concept maybe that we're kicking around here is a little tricky. Have a look at the first diagram that we drew, and I'm sorry I left all those purple circles on there. Let me do it this way. Here's side A. I just drew two. There we go. Here's side A, and that measures 30. And the other option is for us to take side A and pull it in here underneath the ramp. Okay, that's not drawn very well to scale, but you get the idea. So here's side A being pulled in under the ramp. Here's side A when we had pulled it away from the ramp, which is what we did in the previous problem. Here's the rest of side C from our previous problem. So there's all of side C from the previous version of the triangle. What I want you to notice is here. This was side A, which measured 30. That's the rope that we pulled under the ramp versus or away from the ramp. The first time we did this problem, we took the rope length of 30 and we pulled it away from the ramp. Here it is. In this problem, in this version of the triangle, we're going to pull the rope under the ramp, but it still measures 30. Now, if you just look at this triangle, this triangle that I've drawn with sort of my highlighter here has a side length of 30 and a side length of 30, which means that it's an isosceles triangle. And one of the other characteristics of an isosceles triangle, in addition to the fact that it has two equal side lengths, is that it has two equal angle measures, the angle measures that are across from those sides, which means that this angle measure and this angle measure are the same as each other. Do we know either one of those angle measures? We sure do. This angle right here is angle measure B from right here. So we need to go into the left-hand column and grab that B value, 27.131. And I'm going to call it B1 equals 27.131 from first triangle, maybe? Right to the edge of the paper. Oh, I had room. Now, if that's 27.131, then this is 27.131. I don't know how to spell isosceles. You're going to have to look it up. Excuse me. I'm not even going to try. ISOS by isosceles triangle property. It's a little throwback to geometry, okay? So if that's if that's 27.131, then how big is this angle measure? It's the rest of the 180 degrees that would make a sort of a full half circle there. So we should say that maybe we can even label this as B2. Let's see, that's 27 for the first triangle, this 27 by the isosceles. Therefore, B2 equals 180 minus 27.131, which is equal to, I think I can do this arithmetic, 152.869. Pretty sure. Now I'm second guessing myself. 180 minus 27.131 equals 152.869. We did some arithmetic correctly. Nice. Hey, we've got one of our angle measures already. Isn't that nice? Maybe I should put, instead of writing it over there, well, keep it there for the moment. I'm going to write it down here. 152.869. That way I can put a box around it. I love putting boxes around my final answers. I'm going to erase it from over here, pretend that that didn't happen. Nice. All right, so we've got one of our angle measures. We need the other angle measure. Remember, this is actually the triangle that we're focusing on at the moment. One of the angle measures in that triangle is a 20-degree measure. The other one's 152, which means we know 2 out of 3 of the angle measures, which means we can use subtraction away from 180 degrees in order to find the measure of angle C. Angle C is equal to 180 minus B minus A, which is 180 minus 152.869 minus the 20-degree measure. So angle C is equal to, back in my calculator, I don't trust myself with the arithmetic, 180 minus 152 point, that's not a decimal point, 0.869 minus 20 equals 7.131. That is a tiny little angle. But we've got all 3 of our angle measures now. And we know what side B is, and we know what side A is, so the only other thing that we need to solve for is side C, which we can do now that we know what angle measure C is. So I'm going to put side length C in the numerator over the sine of angle C is equal to, I'm going to keep using my A values, A over the sine of A. Let's fill in those blanks. We don't know what C is. In the denominator, we're going to take the sine of our new C value, and I'm going to use the correct angle measure there, the 7.131 degrees, equals side length A is still 30 over the sine of our 20-degree angle measure that we now know so well. We've spent a lot of time with that angle measure. Multiply both sides by the sine of 7.131. Divide by the sine of 20. Let's go into our calculator. I'm going to do this one in the scientific. Hitting clear a couple of times, making sure I'm in degree mode. Yep. And we're typing this thing. Let me put my degree measure in here. Typing it in inside out. So I'm sort of going from right to left here. I'm typing in the 7.131 which I did not type in correctly, 7.131, and then hit the sign button. I've got 0.124, blah, 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 times 30 equals 3.724, etc. Now here's where it gets weird again. Divided by 20, and then hit the sign button. I've got 0.342. That's just the denominator. Let's hit equals. That does the division and gives us 10.8886. I think I'm going to call it 10.89. I'm putting a box around it. I'm confident. I'm still going to go up and check my diagram and make sure that it looks like it makes sense. 10.89. I would say 10.89 is pretty reasonable. Now remember, this C value is only 7 degrees. So really, this C value should maybe be, that angle C should really look like this. And this should be, that's not quite right. It should really look like this, and angle B should be here. And if this is 30 and this is 40, then this being 10, yeah, okay, I could see that. Tough to get these diagrams perfectly accurate when you're hand drawing them, but I think that a side length of 10 and change is pretty reasonable for side C, which means we have found our 1, 2, 3 missing values. That means we're done with this problem. That would make a really mean free response question on a test, wouldn't it? Mean. It's one you might want to practice. I would do one of those a day. And you should be able to find them pretty easily, whether it's in a textbook and you're looking for the ambiguous triangle, other YouTube channels, you should look around. If I find any good ones, I'll post them. My students should be looking in their review packet for the Chapter 5 review. You could look in the ebook, definitely. Publisher-provided videos and other example problems, the study plan. Keep looking around and maybe just go and find all of them right now so you know where they are. And maybe in your notes you could write down page numbers or locations of additional example problems. Put them all in the same spot in your notebook, maybe. Something. Keep those organized. Oh, we're at an hour and 14. All right. So what I'm going to do is, this is actually going to have been, that whole problem is going to constitute part 2. And then I'm going to do these last few example problems as a part 3 of this chapter's worth of video. Not that many pages, but a lot of content, a lot of detail. So thanks for hanging with me thus far. And I will see you in part 3, which you can get to by clicking on this little block that's right below me. See you in a second.